Okay. Can you hear me okay? Okay. So this morning we're gonna use a couple of tools. I think like the objective for this hands-on section is basically show you some of the tools that we can use to gather data sets, and specifically remote sensing data, bring along flux data, and do some processing and some analysis with that. So for today, hands-on section, we use Colab, Google Colab, which is a collaborative coding based on Google, developed by Google. It's similar to Jupyter Notebook and can run, support Python and R languages. And so this morning we will have some hybrid coding. First part will be Python, second part will be R, third part will be in Python again. We're gonna use, yeah, so you have access to the slides. I shared the entire Google Drive folder with all those that send me their Google account. We asked for that, I think like 1 week or 2 weeks ago. So if some of you don't have access to this, to the Google Drive that we share with you, please let us know so we can add you and you can access to all these tutorials. So again, we will use Google accounts for two reasons. Google Drive is where all the material is. So we have this big shared drive that you have access. We're gonna use Google Earth Engine, which needs to be linked to that account. And so, yeah, we will use these two accounts in Google Colab to access to the data and to gather data from Google Earth Engine. So for those of you who are not familiar with Google Drive, but this is where you can find the materials, shared drive, and then you will find the 2024 workshop, remote sensing, and so on. And in that folder, you will see different folders. This tutorial is in hands-on session, and there will be different folder for the different topics, and you will find there the Colab notebook. So basically, you can click on that, and Colab will start. If you don't see the icon of Colab, you probably need to do the double click and select Open With and select Colab. When Colab opens, the first step you need to do is save a copy of this. So you want to work on the original ones, so we can prevent to modify and make the notebook inoperable. So each of you will save a copy on your Google Drive. Colab will create automatically a folder called Colab Notebooks, and the copy will be there. And everything or all the files saved in Colab will be saved in that folder automatically. So what we'll do today, topic one, which I will lead for the next hour with David. We will gather remote sensing data using Colab and Google Earth Engine. We will use Python API to do that. The Python API basically is a nice way to bring and connect Google Earth Engine without actually learning Java, which is basically the language that is the Google Earth Engine is based on. We will do some processing. So the idea is to provide you guys with some utility codes that you can use it for your own data. And here is just a few examples how those codes work. So we will gather some remote sensing data, compute some vegetation indexes, plot some maps, extract some time series, and look at some quality assessment. The third part, we will look at time series over the tower fluxes. Specifically, we have one site for the neon, and the other part will basically show you how to aggregate the remote sensing flux time series together. And after that, we will look how to compare the vegetation index and the flux. In this case, we select NEE as an example. Topic 2, we'll go to regional scale. Here we will use a model to derive and to estimate NE, which is based on the time series that we collected before. And then Stefan will present the high frequency flux specialization to explore the spatial heterogeneity and what kind of information we can derive from there and what kind of assumption we can bring to the analysis. The topic 3 will be led by Paul, and it's going to be a showcase for the baseline imager live imaging of vegetative ecosystem called a live workflow. This will be based on the geostationary operational environmental satellite, which is GOES. And yeah, basically, there will be an entire pipeline that allows you to access those data and create the GPP every 5 minutes over the entire CONUS area. In particular, you will be basically working with specific libraries where all these data are basically stored. Okay, so looking at the area of interest, we select this tower flux with UN near University of Notre Dame Environmental Research Center. Here we'll see this dot basically represent the tower location, and this is an area that we basically consider for looking where we're looking basically the spatial heterogeneity, and compared to the single point or single pixel over the tower when we are looking at the time series. Okay. Okay, so let's start with the tutorial. I see in chat that some people don't have access to the folder. Maybe some of you could add those accounts to the folder. Okay, cool. Yeah. So I'm gonna start with the topic 1. As you see, and we start with the data gathering. So the idea here, I will go through so you can see a little bit of the steps. I give some explanation what is going on, but the idea is basically you also run it personally and see if everything works out. And if you have questions, we are here to answer. If you have issues, please let us know. Some of us can come to you and help out. So again, first things to do is make a copy of this notebook. So we are gonna do exactly that. And we're gonna open the copy. and we're gonna work on exactly that. Now there's a couple of packages needed to install, so that will take a couple of seconds. For the topic 2, there's actually big packages to install, so maybe we can install those during the end of the breakout session, so we don't lose too much time during the session. Okay, so they're gonna ask you, give the permission to this knock to access your Google Drive file. You connect to Google Drive file with your account. Now that we have access to Google Drive, if you go on the left panel and click on the folder, you see that you have a folder called Drive, and if you dig in, you can see that you have access to your drive and the shared drive, and you have, well, I have several shared drive, but you definitely can see your 2024 workshop. So, this is just to check that everything works out, because the notebook has links to the data set in that shared drive. So if you don't see this, it's problematic, but we can fix it. The next step is the initialization of Google Earth Engine, and here you have to add your account, which in my case would be just my name and surname. All right. Okay, so now it's time to actually dig in the data sets. So in this part, we will look at how Google Earth Engine can obtain some Landsat and MODIS data sets. And then the idea is to consider area surrounding the tower, the flux tower that I mentioned before. And we have the lat and long for the position. And so we will gonna use that information to basically delineate the areas where the area of interest for the imaging. So first step is basically importing the entire collection. These lines basically give you access to the entire collection of Landsat 8 in this case. This is surface reflectance and the MODIS collection. And this is a collection that has PAR and LAI at 500 meter pixel. So far we have access to the entire library, which means that spatial and temporal dimensions. What we can do next is apply time filters to say, okay, we want to limit the data set to specific time period. We also have spatial filters. We can provide geometry. We can read the shape files and say, okay, use this information to then crop the collection only on the area that we are interested in. So as a period, we wanted to just look at 1 month in 2019, August 19. So we create a filter that way. We create a geometry in that way. So these lines of commands are basically the Python API that interface with the Google Earth Engine. So I mentioned that we have this area surrounding the tower, about 6 by 6 kilometer. Another example could be 60 by 60 kilometers. This is just an example to, extract different areas centered on the tower. So you have different view of the landscape at different scales. Now, what the next step is like apply these filters to our collection. And we use the command filter date and the filter bounds, where we basically introduce the parameters that we set up in the previous cells. And we do both for Landsat 8 and the MODIS. Now, what the next cells basically gives you some. We define a couple of functions where we want to check what are the date of acquisitions for both Landsat and MODIS, and then select dates that are close by to compare the images. And so if we go through these cells, we see that Landsat, we have only 3 days, and for MODIS, we have way more. We know that MODIS is collected every 4 days, and so that's why the temporal resolution is much higher than the Landsat. And we select for Landsat the 2nd of August and for MODIS the 1st. So we talk about filtering the spatial area and the temporal.
Are people having a hard time getting on or connecting to Google Earth Engine? Yeah, I think that many people are stuck.
Okay.
Stuck here. Where I was stuck. Are people stuck with the authentication initialization part? Yeah, I mean, I think, yeah.
Okay, can you raise your hand if you're stuck at the Google Earth Engine? Okay. Do you know if you have an account with Google Earth Engine? You set it up already? Right, and you're using your Google account and Google Earth Engine are connected to the same account. And you are not able to oh, okay. No. So so one arrow that I just saw here is basically, if we go back here, as you see, there's no @LBNL or @Gmail. This is just the first part of your account. So if you add something like this is wrong and won't work. Sorry, I can't hear you. You don't have an account with Google or Engine, or? So the project usually create automatically when you create your Google Earth account. Can you go to your Google Earth Engine? It's open. Yeah. So this is your name. You don't have, okay. So yeah, you don't have the, so go back to the. Did you go through this? You just made it. No, I use it, but I don't know.
I think the only thing that you can do is to identify the number, the name of the project. If you go to the login screen here. Yeah. And just, identify what you have to choose. There. And then. Depending on, probably you can use the existing one. Yeah, but just go ahead. But yeah, I just want to show you how to identify your project if you kind of forget the name of your project or having problem. I think you can do a demo with your laptop. So probably start with login of Google Earth and then.
Yeah.
Yeah, because people just forget what they have named.
Okay. So I can.
Oh, well, actually, I have. Okay. So I have changed mine. Oh, sorry. I forgot to make a copy.
So this is mine, right? Yeah. Oh, this is your.
No. Actually, I forgot to make a copy and just made a change on the original one. So yeah.
Okay.
Just changed. But yeah, I think it's a good idea to just show them like from the beginning of Google search engine.
Okay. Yeah.
At least how they can identify their project name.
Yeah. Let's do that.
So just Google Earth.
So let's have a step back here. I see some people having problem with the Google engine. So I just logged in my account, and this is basically the name of the project you had to bring in the collab. You see, this is the account here, which is basically linked to the Google account that I've been using, and this is the project that if you don't have a project, you can register a new project, I will select unpaid use, project type, doesn't really matter. Create a new Google Cloud project. It must be different from the previous project, and then you just continue and create the project.
If they can't make a project because some domains don't allow you to, I think you have to go into a private window to be able to log into Google Engine for a different, because there's the internet, the cookies will hold on to your previous account.
I see.
It's hard.
Okay.
But we got it to work.
Yeah. Okay. Yeah. So I think what I would do is probably going through this notebook. The datasets are already saved in our Google Drive. So you won't need Google Earth Engine for the next part of analysis. So I would likely to finish this part just to explain to you. You can follow on the screen for those that have still issues. And then I can come back to you in the breakout session, sorry, during the break, and then we can figure that out. But at least you're looking here and get some a little bit sense of what is going on the gathering of the data sets. So I would continue with the demonstration here. All right, I think we were. Okay, we got the so we got the data acquisition from Landsat 8 and MODIS, and again we can see the different temporal resolution of the two satellites. What we can also do is to make operation on the bands. For example, create some vegetation indexes, and so these cells basically. Well, before that, I forgot. Several satellite data sets needs to be reconverted and apply a scale factor, because Google Earth Engine just store the data to optimize size and space. And so Landsat 8, for example, have specific parameters that needs to be applied to each band to bring it to the original range of values. And so we will do that. Beside applying scale factors, we, again, as I mentioned before, we can perform a bands operation. In this case, we are creating 3 specific vegetation indexes: NDVI, NRV, and EVI. And the next cell here is basically we apply those bands operation to our collection. From here, basically we obtain a collection. We have a 3 acquisition of Landsat 8 over the area surrounding by the Flux Tower. The next thing is what we want to do is select a specific time, we want basically to plot one of these acquisition. And what we can do is, for example, select specific bands that we want to plot, select specific dates. In this case, we add the acquisition on the 2nd. And to be able to plot, we need to apply a reducer, which is like a function that basically flat the entire collection. Now, it's maybe counterintuitive, but what happened is that we are changing the type of data objects, which allows us to basically go from an image collection to image, and we can then plot the data objects. Looking at the data structure after this, applying this, we can see what are the bands that are being collected. And we can see that we have all the different bands, the vegetation indexes, and also the quality assessment pixel. We do the same things for the MODIS. We see that we have the FFR band, we have the LAI band, and also some quality control band that we're gonna use later on. For plotting here, for you, I put like a histogram function, which can be useful to stretch the image if it's not really clear. So we go ahead to run that. In this cell, we apply the stretching, the histogram stretching to all the bands for both Landsat 8 and MODIS. And then the next basically bunch of cells is there for plotting the Landsat and the vegetation index. Now, for example, here we can bring a composition of bands and give like a sense of RGB. Is the histogram stretching maybe, you know, is not the best to bring a true RGB image. We can also see from here, for example, there are some clouds, and so that messed up like the histogram stretching. So that's why maybe the color are looking funny. But nevertheless, we can look at see the spatial variation of the area and some features like the lakes and some variation across the different land covers. The next step, we want to plot the NDVI, and the NDVI shows like this. What we can see is that using a red, yellow, and green palette, we see that it's pretty green all over the place. So the first intuition is like, okay, NDVI is kind of at the maximum level, so kind of saturating a little bit. And we have some weird signal on the lakes that might be a signal related to maybe some element on the water surface. If we plot the NRV, we see already that the spatial heterogeneity is definitely better modeled in terms of greenness. And then we see all the areas. Yes. Sorry, I cannot really hear. Maybe. So if you have a question, please check with these guys. So. And the next, we're gonna plot the EVI.
Hey, Nicola, just a question in the notebook, in the plotting VIs.
Yeah.
At least two of us at the back, we are getting this error that a parameter low is required when we try to plot the composite image thumbnail. When you import the further up. Keep scrolling further up.
Say again.
Oh,
further up.
Scroll further up. Yeah. Yeah, here. So this particular function, well, you have the same thing. Well, we are getting an error that.
How many of you guys are getting an error here? Or.
Well.
Hi, Nicola, can you hear me?
Yeah.
I had the same issue, so I just reran the code from the beginning. So it was solved.
Okay, we'll try that. Thanks.
Yeah, no problem.
Again, if you have like issues, please check with Stefan and Dave. If there are concerns, we can also, you know, keep talking during the break. And so the next one would be the EVI, and we see that is similar to the NRV, although the NRV seems like more representing a bit more the spatial heterogeneity compared to the EVI. The nice things is that lakes, clouds, and shadows are actually at lower values here. So they can be masked from the analysis. And here we can plot the MODIS. Of course, we have a pixel that is 500 meters, so it's not really, spatially it's not comparable to the previous. We see that, you know, we still see the features and the spatial variability in the LAI. We see also some black areas. Those are probably masked area from the LAI, where LAI values are not, yeah, they are probably masked values. As another example, we're gonna basically do the same, bring the entire collection, but then apply it to a region that is bigger than 6 kilometers, and we go to the 60 kilometers. So just to give you a sense of how can we, generate multiple data set at different scales without running, again, the entire procedure. And so here, for example, is, again, the RGB for the 60 kilometer. We see there's a lot of clouds going on in this part of the image. And so the next part, basically, we have a couple of functions that look at the of the quality assessment for Landsat, for both Landsat and MODIS. Again, to check this quality assessment, you really need to go on the Google catalog specifically for each data set, and there you will find all the information. You will find the links to those catalogs at the beginning of this tutorial. So those links basically bring you at the page of each of these data sets with all the information needed for that. So we applied some masking based on the quality of the pixel, and now we're gonna replot again the data set. So this is basically the cloud has been masked, and the black here is basically what is left from the Landsat. Hard to see the real colors here because the range of values bringing also the masked area that can be easily modified and use only the pixels that are not being masked to actually compose the image, but this is just an example. We can replot the EVI, and then here you see EVI computed only for the area that has been, for the area with the pixel with a high quality pixel, and same for the MODIS. Now you will see the MODIS and the Landsat differently because there are 2 different days. There are 1 day difference. So we see that the clouds that was on the 2nd, they are disappear on the 3rd. Although MODIS has probably other things going on here. Could be more clouds, or could be that the landscape has very low LAI values that are not in the range. So the next cells, basically, they want to save all these data sets as GeoTIFFs, and you can use this to save the entire data set. For example, here we are saving the entire Landsat with all the bands and the quality pixel for the 6 kilometer crop, and in this one for the 60 kilometer. So the nice things here is that you can actually look at the task of the status. The status for saving says here complete. And so if you click this link, you can actually go and this is gonna have, basically it's the link in the folder, bring you on your personal collab, and you will find all the data set that has been saved directly there.
Mine shows already. Is that different from completely?
Yeah, so, interesting. Already means that it's still working on. So for example, if we go for the 60 by 60 and we click this, the state is ready, but it's still working on. So this is gonna take a couple of minutes. You need to wait for that. And when it's complete, you basically means that the project has been saved on your Google Colab folder. And if you click again, now it's running. And so if you run these cells a couple of times just to keep track of what is going on, this function basically keep track of the last task that you have been running. So if you run all these cells at the same time, this task is always related to the last task that has been that has started. So for example, if we click again, it's still running. We will probably wait a little bit more to get that file saved. Yeah. So moving along with the structure of time series. The idea here is basically to look rather than the spatial, extract the spatial crop, we are looking to extract a time series over a specific area. So we are defining the location of interest on the flux tower. Again, here we are defining the time period for our time series. I selected 2 years of data. Again, we are importing the Landsat 8 collection. We are applying the filters, the date filters, and the area filters. Here, I'm still using the 6 kilometers because I also want to. It seems like the object type object needed to run specific maps needs to be an image, and so I use a small area first. I compute the vegetation indexes. We can see that we have a 51 selected area over the entire these regions. And then if we using the get region function, we consider we can extract the entire collection for that point. We need to provide the size of the buffer. And so here is basically the structures of our data. We have all the entire data set, all the bands, the metadata, and the quality pixel and the vegetation indexes. Now, what we want to do is do some analysis, right? So at this point, what we do is basically convert this data structure, which is becoming a list using this get region and the get information functions, transforming this image into a list or array data structure. We can use a function to convert that to a Panda data frame. And using pandas, we can start to do some analysis. So that is the function to do that. We apply that to our list. We see the shape. Now, going from the area of 6 kilometers to 1 point, we see that we have only 52 acquisition with good data. And here is basically our table. This can be exported as a CSV file, which we will do later on. And here is basically the cell for plotting the time series. Now, what you see here is basically the time series of NDVI, NRV, and EVI. Is interesting that, I mean, we see the seasonality somehow, but we also see a lot of noise between the growing season and also in the winter period, which tell us a little bit that there might be some issues with the data there. And so here again, we perform quality assessment for all the time series. We see that we go from 52 to 16 good acquisitions based on the quality assessment. We replot the time series and we obtain something like this. And so now you see that there's a better seasonality, and all the pixel in winter time has been zeros because probably related to clouds or other phenomena going on. At this point, we can save the data frame as a CSV file. And again, you will find this in your Colab notebook. And we export, and we do the same basically for the Modis time series. So the exact function, now they are applied to Modis. We see 185 acquisitions. We perform quality assessment. After the quality assessment, we have 60 acquisitions. We go from the Google Earth Engine type of object to data frame. And then we plot a Landsat and Modis overlap together. And this is what we obtain. So we see that Modis LAI has much better spatial resolution and follows much better the seasonality of the point. Of course, we are comparing 500 square meter pixel to 30 square meter pixels. So there's a spatial variation there. So that is, of course, needs to be taken in consideration. But this is just to give you a couple of tools where you can gather data, time series, and plot together and decide where and when gather those data. And with this, basically, we save the CSV file to Colab Notebook, and basically we have the time series now ready for the next part of the analysis. So the next couple of, the next part of the analysis, I will let Dave to lead this part. Again, for each of these notebooks, please save a copy in your drive and use that. Okay. So for this notebook, you don't need Google Earth Engine, but you need the Google Drive working. So that's good news for some of you probably. So the first thing, again, okay, let me start again that. Do you want to use your computer?
Either way.
Okay.
We just get them started.
So this notebook will need to download some of packages. So this will take approximately 10, 30 minutes. So the idea would be to run this cell and let her go. So here is saying to upload new version of some packages. I just put empty line, so there's no need to do that. It should work fine anyway. So this is gonna take a little bit. And so if you are able to run that, we can then go into break, and I can assist those that have some issues, and then we can restart again after the break from the analysis here with Dave.
We're about to start the second portion of the tutorial. So hopefully everyone was able to kind of get started with some of the dependency downloads. Those can take a little while. Mine's showing that it's about 13 minutes for that portion. I think a lot of that is due to the geospatial libraries that need to be downloaded for this portion. And the fact that this is running in a Python runtime, but we're using kind of this magic R. So in case people are unfamiliar, in Google Colab, here you can see this RPy2. This allows you to run R code within the Python runtime. And at the top of each cell, you'll see that we have this double %sign followed by a capital R. This just means that that cell is running R code as opposed to natural Python. So this first section that we ran before the break, we are downloading some of our dependency libraries. We started with the Ameriflux R package, which we have the author here, like Halson is one of the co-authors of the code. It's a great package to interface with Ameriflux and download data on the fly, which is what we'll do here in this next portion of the code. So all the Neon sites are co-registered with Ameriflux. And so you can explore the Neon data via the Neon data portal or via the Ameriflux data portal. And one of the nice things is the data that we provide to Ameriflux is then processed using the FluxNet processing or utilizing OneFlux, following Gilberto or Pastorello, his paper from 2020, I believe. But so there's more information below if you want to learn more about the processing that goes into the OneFlux processing. So at this stage, we'll basically run. We'll provide a temporary directory, and we will download the data and we'll extract, we're going to use a weekly average time frame for this study because to try to align with how often the satellite overpasses for the MODIS and the Landsat. Weekly seemed like kind of a middle ground. So when we download the data, and then we basically combine that and unzip all the files so that they're available for us to read in. In this next step, then we will change the missing values to nans, and then modify the timestamp so that it's kind of the middle of that period for the weekly average data. So this allows us to kind of do some index matching between the time series data and the remote sensing image that we have. And then you can see we just list all the variables because we're using the full set of the FluxNet data. There are quite a bit. I think there's over 300 something variables there. For the tutorial today, we'll be focusing on just NEE, or the Net Ecosystem Exchange. And even if we look at just Net Ecosystem Exchange, there's probably 20 or more NEEs available in this file that are using different quality procedures, different types of U-star filtering, also daytime versus nighttime. And then we also have this kind of reference value. And so here I default to the variable U-star filter and using the kind of reference value, so that the best kind of model version of the NEE. And we'll utilize that for the analysis that we're doing today. If you want more information about the Passarello et al. Paper, you can follow the link here. And so in this step, then we'll read in the Landsat and MODIS data that we collected as part of Nicola's tutorial. And then we determine that time step, the index of the time steps that closely match each other. So we look for the timestamps for the flux time series that match closest to the time series of remote sensing data that we have from our pixel at our tower. And then we subset and combine those data frames together. And here you can see now we have kind of a clean data set of the time, the date time, and then our vegetation indices that were calculated and cleaned by Nicola. And then our NEE, our gap filled NEE values for those same timestamps. So in this next step, then we can kind of plot and look at the relationships between our vegetation indices and the flux data, and then derive just some simple linear models and see how well we get a fit between those. And you can see for NDVI, we have a R squared of around 0.54. And we can definitely see some scatter around that, and some grouping kind of at the extreme scales of the scatter plot. So let's try our next indice. Let's look at EVI, for instance. And we can see that we get a slightly better relationship here, where we have an R squared of like 0.61. And you can see that we get a tighter fit to our regression. I have to point out that we're using just a simpler linear regression here. In practice, you might want to use a different model, whether it's a kind of a machine learning model, but in this tutorial, we just want to show the principle of fitting a model to your data and then projecting that to kind of a flux map area. And so then last, we'll look at the NIRV and explore that relationship. And so now that we have these three models, it can be, we could either use the R square value to determine which model to use, but there's also other methodologies that we could explore. Sorry, I forgot, we'll also fit kind of a model to our LAI data. And here we can see we get a slightly better R squared, 0.67. And that's just due in part to the higher temporal frequency of the MODIS data versus the Landsat data. We have just more points to fit to it. But we know that the spatial resolution is not as good for the MODIS data. So, we would like to capitalize on the higher spatial resolution that we get with the Landsat data. But we'll look at both going forward. But to evaluate which model was performing the best for the Landsat vegetation indices, we can use an information criterion. And here we have a limited amount of data, but they're all fit with the kind of this least squares regression. And so we can explore those against one another and how well the fit perform for each of those. And using this AIC approach, you want to look for the one that has the lowest value that indicates that it has kind of the best model fit. And in this case, we see that EVI performed the best out of these three models. And so now we can proceed with the next step of taking and reading in our 6x6 kilometer imagery from Landsat and MODIS that we got during Nicola's tutorial. So we're just reading these in from the Google Drive where we wrote them out earlier. And we can kind of see the difference in the spatial resolution that we talked a little bit about in the first tutorial. We can see also the lakes are highlighted at a pretty extreme value in the EVI index. And next, we will just apply that linear model that we calculated between the flux time series and the remote sensing time series, and predict across that spatial domain what the fluxes would be based off of that linear model that we created. And like I said, this could be any model. We could substitute other models, but this is kind of the general workflow that you could use to project your fluxes based on the information you have to the broader landscape. And here you can see the plot of the flux maps from the Landsat EVI, and then from the MODIS LAI relationships that we derived. So we've touched on a couple of those kind of pitfalls or challenges with this approach. And here I'll hand it off to Stefan, where he'll dive into some of those in more detail and how we might be able to address those. Sure. Yeah. It's a little.
We'll manage. Let's get this stuff out of the way. You good? All right, how is everybody doing so far? Everybody have fancy maps on their screens? I hear like you're sounding, yay, we all have maps. All right. Well, let's take a closer look at those maps and see whether they truly are what we believe them to be. So the next subsection we dubbed pitfalls and challenges, because we did a couple of things, or we made a couple of assumptions that we did not necessarily make explicit, and that allows us to explore them. So the first section is about checking our range of values. So essentially, when we had two data sets, right? We had one data set between Flux and EVI that we were doing a linear regression on. And then we were using that linear regression and apply it to a whole map of EVI pixels that possibly has a larger or a different range of EVI values. How comfortable are we that our linear relationship is valid? If we're either interpolating between different areas of EVI, I'm going to scroll back here so it's easier to see. So here we had a range of values. This is LAI, NIRV. We're going to continue with EVI. So we're going from roughly 0.2 to 0.7 in terms of where our regression should be valid. But at the same time, when we look at the EVI map, we have a range that goes almost from, that is EVI, from 0 or actually slightly below 0 to 0.8. So we would actually be predicting or projecting into a value range that our linear regression model has never ever seen. Are we comfortable with that? Do we think that the greenness relationship also holds over water, for example? Are we maybe more comfortable by saying, okay, we don't extrapolate to water because water doesn't have as much chlorophyll like plants, let's say, but we're still comfortable to interpolate between our data points because we were somewhat data scarce when we were creating our relationship. And so that's the next part that we're going to explore in this next code block. So let's go down here again. So when you execute this block here, it should tell you what are the ranges in the data that we used for the linear model. So it's 0.16 roughly to 0.77. And that's quite a bit narrower compared to the EVI map. So let's see what happens when we actually remove those pixels that are outside of our linear regression range and what happens to the map. So that's what's happening in this next little block here. You can click on that as well. The only thing it's going to do, it's probably going to update the figure that you're seeing here. And what do you see happening here? Anybody? On this new map here, what looks different?
The water areas are removed.
Exactly. And what are those white? I think that's online, right? And what do you think those white areas are?
Water bodies.
Water bodies, exactly. Yeah. So those were mostly water bodies, I'd say. So those were quite a few pixels in the range below roughly 0.2 EVI that our linear regression model that we never trained it on. So we removed them in order to be consistent, for our map to be consistent with the range of our training data. Thank you. All right, now we can use this map that is now thresholded for pixels outside our training range, and we can reapply our linear regression model, which we're now a bit more comfortable in. It's a bit more trustworthy to work within the range of values that we build it for. So if you execute the following code block, that's exactly what's going to happen. You're going to see a new flux map. And
what's happening here now when you look at the range of values? So you might want to spend a minute going back and forth between the map that you create here now and the map that you previously created, and let me know what you find. Anybody has a result yet? Are those the same range of flux values? If you look at the color band here on the right-hand side.
Yeah, EVA flux value of -3 value, which is not in the EVA range.
Yeah, the range of value is somewhat contracted, right? Like previously consistent with us reducing the EVI range that we're working in, the range of flux values that we see here on the right-hand side in the color legend also reduced. All right, so that was the part in terms of a challenge or potential pitfall to ask ourselves, whenever we are creating a relationship, to which extent or within which range is this relationship valid if we apply it to a data set? Now, the next part is about exploring to which extent our flux data that we're going into the relationship with actually satisfy some underlying assumptions. So yesterday, Ankur, myself, others talked about mass continuity and things like a mass balance box, which is underlying the eddy flux technique. So essentially, instead of having a literal chamber out there, a physical chamber that you either open and close or dynamic chamber, but a control volume nonetheless, right? Instead of having a physical control volume, eddy flux assumes a virtual control volume. So a control volume that's not visible, but that nonetheless, you're able to track the exchange of mass and energy across all the phases. It's just that we are very severely simplifying the equation, but that's what we ought to do. And those simplifications, they make certain assumptions, and what we're going to check in this part of the tutorial is whether those assumptions are fulfilled. One of those assumptions are, you might have heard about it before or not, termed stationarity or heterogeneity. So you really want your flux system to, in order to fulfill those assumptions, to measure one land cover and not a constantly varying mix of land covers. And so that's the first thing that we're going to look at. And then we're going to explore whether or not that actually has an effect on the flux and on our assumptions and in our relationship. All right, so what we do here, what we prepared is this is not half-hourly fluxes anymore, but it's that same 1 week time period for which we created the map, but expressed in 1 minute fluxes. So it's that high frequency flux processing that we talked about yesterday. And that allows you to look into much more gradual changes of land cover, of EVI as is experienced by the flux tower. So when you click on that part of the tutorial here, that is the data set that it is going to read in. So minute resolution flux, quote unquote, air parcels. And we again have here for reference our standard FluxNet NEE reference, but then we also have a few other things, such as the 1 minute flux called response here, and then various quantities inside the footprint, enhanced vegetation index, not over a map, not over a pixel, but over where the wind is coming from right now. And that's constantly changing every second, every minute, every hour. And so that's captured in this data set here as well. Land surface temperature, a couple of flavors, and then land covers. And that's something we're going to focus on now to keep it a little bit higher level. We're going to check out, does there actually variation occur over the week, over half an hour, that might actually fail us in some of our eddy flux assumptions and what we can do about it. Was everybody able to read it in? Was anybody not able to read it in? Please speak up now. Deafening silence, so everybody was successful. I like it. All right. Let's keep on moving. Okay, so the first thing that we do here is to pick, for starters, one land cover here, wetlands, and the entire week. And we're just plotting a histogram and check, do we essentially always have the same land cover contribution here at the bottom? So we would want to see a single bar here if you want. So, oh, the towers always be seen 40% wetlands, or in the perfect case, actually it's always seen 100% wetland because that's our wetland tower. But you know, at a minimum, we would want to see maybe 1 or 2 bars. And so when you can run that box here right now, and it should evaluate for wetland, and that's a foregone conclusion because we already did this here in tutorial. We actually see a bimodal distribution, and it's certainly not at 100%. So things seem to be sloshing around and shifting. And what kind of imprint does that have on our fluxes as a spatial control versus a temporal control? Because oftentimes we think, oh, yeah, fluxes vary with, say, incoming radiation and maybe with different EVIs, but then even the EVI imprint on that will change because when you have different fractions of wetland and forest, your EVI will change as a result of that as well. Now, what I'm going to ask you to do, you can actually go into the code, so you not just have to like click start and stop and things, but you can go in here where it says histogram, know your data, KYD $wetlands, and you can substitute wetlands for a different quantity. And you have several of choices here. You have deciduous.forest, open.water, and so forth. And let me know what you find. I'd like to know whether these are all bimodal or how they're normally distributed. Maybe there is a land cover class that's actually fairly homogeneous. I give you a couple of minutes, and then I'd like 1 or 2 people to maybe report their findings. All right. Did anybody do, let's see, what did we have available here again in terms of land covers? Who did deciduous forest? Anybody did deciduous forest? Oh, Sunath, what do you find? Normal distributed? Is there, but it's neither uniform nor is it 100%, can't get 100%, I guess, because we're already losing to wetlands, but that was normal distributed? Okay, cool. All right. So it's already complement, bimodal, normal. Did anybody do or find anything for open water? Oh, Sunath, you're productive. Go for it. 0, yeah, right. Because those water surfaces are a bit further away from the tower. So the wind speed, probably particularly at night, is only then the wind speed is actually high enough to give us information from these land covers that are a bit further away. What else might be in there? Other forests. Developed land was interesting because I think there's a couple of roads nearby. Did anybody develop land? So it's kind of skewed, a skew distribution. Cool. Thank you. And I haven't even tried that before, but we kind of already get a sense. We're a bit all over the place, right? We have, there's no clear pattern, no clear distribution. In particular, in sites like these, we've seen from the map, that are fairly heterogeneous. You have water surfaces, you have wetlands, you have a little bit of everything. How to tease that apart. Thank you so much. Then, let's see, this was that part. Now, this was the part about understanding, hey, okay, what happens throughout the week? And we can do that with our standard data products that we can download from Ameriflux, from Neon, from Fluxnet, and we run a footprint model and extract the different land cover contributions and trying to account or maybe a portion for that. How Sen, you gave a great talk about that yesterday, how it's becoming possible to separate fluxes for individual land covers. Now, with regard to eddy flux assumptions, though, what's the part of interest is what happens within the half hour, because within the half hour, that's where we are supposed to observe a homogeneous surface or ecosystem. You want for a while only forest, or at least the same fraction of forest in there, and this not change all over the place. And so this is what we're going to do in this next section of the tutorial. And it's going to do a few things. So first, it's going to do that histogram that you've seen, but now it's going to do that for an individual half hour. So now you have two choices. You can pick the land cover that you're interested in, and you can pick one out of 432 half hours that we prepared here to take a closer look, a more finer grained look in here. And where you can adjust this is here in that second paragraph, where it says index, IDX, know your data, KYD. There you have that choice. You can set that number here to different settings. So anywhere between 1 to 345 in this case. And down here, you can then choose different land covers. And while you do that, now I'll give you a quick rundown what I found for this particular example, and then I give you a little bit of time to play for yourself and see what you find, and I'm going to ask some questions again. So what we find for this particular half hour, which is around noon time on August 12th, so that's centered in time on the MODIS scene on the Landsat scene that Dave was earlier presenting on. That's kind of the distribution that we find throughout the half hour. The land cover shifts due to a change in wind direction and change in wind speed from 10% to 60%, so fivefold essentially, so severe change. And related to that, let's see, this is actually how it changes over. This was just a histogram. Here we see how it changes over time. So essentially we have very little wetland in the footprint, and then we have a lot of wetland in the footprint suddenly. And related to that, we see a change in flux that seems to be somewhat anti-correlated in change of carbon flux here. And now what's interesting, typically you don't see that flux pattern. So for a standard half-hourly product, what we get is that red line here. So minus 20 micromole per meter square. And if we actually look into the finer grained patterns and account for them so that eventually our control volume is not leaky anymore, and we'll see more about that later, so that more of our eddy flux assumptions are fulfilled, we gain back some of that missing mass or energy, depending on which flux you're looking at. So the average that you see here, the blue average, is actually quite a bit lower. And so what your task is now to also evaluate that for different time periods. So you can choose different records here. When you go up here, you can choose a different record instead of 178, and you can choose a different land cover. And I'll give you a couple of minutes, evaluate 1 or 2 or 3 of those, and then I'll ask around in terms of findings. All right. Did anybody find something interesting? I see a raised hand there. Maybe not. Are you raising your hand? You did not find anything interesting? No? Oh, I got you. I'm sorry. How are things looking online? Did anybody try something out there? Feel free to unmute yourself and report your findings. So I just forwarded mine here to give an example by one index, so the next half hour. And here we see a change again from 50, 60% wetland in the footprint to 30% and back up to 50%. And then a similar, somewhat anti-correlated flux and a similar increase in flux if we actually consider those short-term variations. Let me know if anybody else wants to report out. I give us another minute and then I'm going to move on here. Go ahead. Yeah. Do you want a mic? Do we have one?
Yeah, just a quick question for me. Could you explain again that difference between what we're seeing in the blue line versus that red line in that graph, the last graph here?
Right. So what we see in the red line is the standard half hourly flux that we download from FluxNet, from Ameriflux, from Neon. And that is composed of the average properties throughout that half hour. So when we do that, we get a lower flux as compared to when we actually resolving the, in part, land cover related flux changes throughout the half hour, and then taking the average of that after resolving it. So the blue line is the average of that. The blue solid horizontal line is the average of that blue traced dashed line that is actually time resolving. So when we resolve features and changes in features in space and time, what we see is that we're actually starting to be able to recover, well, both. Yeah, I'll leave it at that for now. We're starting to recover some of the missing flux. Any more questions? Any more thoughts, feedback? All right, let's move on.
Like, what if I don't see any red line in my graph?
Come again, please. What did you say?
Like, I use land use cover for deciduous forest where I don't see any red lines in that graph. Like, what it actually means.
Yeah, that's a great point. And thanks for pointing that out. So to your question earlier, actually, what is the red line versus what is the blue line? the red line does not in any way consider underlying land cover changes. We also haven't yet apportioned the blue line for land cover for wetland specific flux or deciduous specific flux. We'll do that process later down here, or process that allows you separating that. But what we look at here is essentially the effect of a changing land cover composition on the flux, so that the flux is not just a property that changes in time, but also where the wind is coming from, essentially. And so that red line, you shouldn't have to change that in the code. When you go, let me go back up in the code here. So this here is the red line, the standard 30-minute FluxNet product. Because this is not land cover specific, you don't have to change that. It's going to be the same line, right? Because there is no separation land cover, which is something we're beginning to argue for. Like, we actually would have to take land cover into account, but we can't just yet. The standard product doesn't account for that yet. Any other questions, comments, findings? All right, let's move on. So now what we've seen is that either wind direction or wind speed is constantly shifting. It's not constant in time. It's not constant in space. And what that amounts to in terms of the assumptions that go into eddy flux, into the data that we use, what that amounts to is essentially a leaky control volume, which is what you see here on the left-hand side. You don't want that. You might have heard of advection, of things like that, of non-stationarity, of homogeneity, inhomogeneity. So it's all these kind of effects that are folded in together. Say if you have a wetland patch that's outside your virtual control volume, so outside your virtual chamber, so to say, in the field, but you constantly have cooler air from that wetland leaking into your chamber, that's going to skew your result. And if those fractions constantly change, it's going to skew your result in a constantly changing fashion. That's really hard to tell apart from temporal controls, for example. So the idea here is, hey, is it possible to use this finer granular data, this minute scale data, to tell these apart, to actually sort out the mess, if you want so, and stack, like trace these individual minute flux parcels, trace them back to their origin, stack them neatly inside the control volume and outside the control volume, so that we can now count them out and properly fulfill our assumptions underlying eddy covariance. So that's kind of the underlying premise of continuing with the minute scale data. So for that, what we've prepared for you are the products that result, these half-hourly flux maps that result when doing exactly what you see here. You trace these individual parses back to their origin and stack them. And this is what you can read in here in the next paragraph. And Dave, you actually put some, was it in this area? I think you put in some really cool technical features that we might want to highlight. I'm going to hit the start button now, and then I'll let you explain maybe. Was it here that where you were saying? Can I, once I started one of those boxes, can I stop it? So just click on that button there. So that one is the unzipped one should be there. Yeah, it's just going to take a while. That's why. Yeah. Okay.
I guess just to talk a little bit through the data munging that's going on here is, we wanted to make sure that we're aligning. The FluxNet data product is in local standard time, and the Flux maps that were generated from the Neon data are provided in UTC time. So we take that time difference and then we apply that on the data to make sure that we are aligning our time periods for the FluxNet data and the Flux maps that we're looking at. So it makes it pretty easy to do that with the Lubridate package, and you can just use the interval to try to find that overlap between the two time periods. So.
The part that's taking a while right now is that these maps are individually new zipped here. And I forgot to comment out that unzip line because I already unzipped them previously. I think actually for all of us, so we can directly read in simple CSVs. But this point is already running, so we might as well not interrupt it. So while that is running, feel free to ask any questions, share any thoughts you might have, maybe any other findings. Leila, I see you. Can you unmute yourself?
Yes, can you hear me?
Yes, we can hear you.
Okay, Stefan, I'm having some issues understanding the concept behind the second part. So it's the box that you draw with X, Y, Z representing the flux footprint, or should I forget about the flux footprint and you are introducing something else?
So when you go, great question, Leila, thank you. When you go back to the fundamentals of eddy covariance, there was no flux footprint, there was a control volume. So that's what we're looking at. That's what we're methodologically supposed to do, is to measure essentially within a chamber. It's just that the chamber doesn't have actual walls, but we're counting, we're supposed to count how many molecules are being transported across each face of that cube or of that control volume. And then came the realization, oh, dang it, that's not actually what our flux towers are doing. Like we can approximate that a bit better with aircraft or sometimes with scintillometer and other laser measurements that measure along interfaces, but not with measurement at one point. And it becomes even more complicated by that organic plume-shaped kind of flux tower footprint that's moving around all the time. And I don't think I have my other presentation on here that kind of superimposes both concepts, the plume concept and the control volume concept, but we somewhat have to bring them together. And that's what this process is doing. So what you see on the left-hand side is essentially where it says classical EC. That is essentially a view of how a flux footprint can also look like when you pixelate it into individual air parcels. And on the right-hand side is then essentially when you trace back those individual contributions to your origin. Leila, does it help at all relating those two concepts?
Yes, it does. Thank you so much.
Yeah, you bet. And I think on my other computer, I do have that slide from yesterday that if the code box is still running, I'm going to pull that up. But let me check first.
So yes, just an extra comment. So what we are doing here is trying to track back the origin of each of the molecule particles that originate the flux.
That's right. to the surface feature where they actually belong to, if you want so. Because once you know that, you have the flux signature of that surface feature, and you have the optical feature, such as EVI reflectance and so forth. So you can relate them together much more closely.
Okay, so one extra question. Can we do that regardless of the nature of the concentration? Like, is it be the same if we use it for a mass or a heat or any other type of flux?
Great question too. So general answer, yes, for fluxes of non-reactive species, of passive species. So if you have volatile organic compounds, if you have NOx, air pollution, things in cities that actually are reactive, or NOI, then that does not necessarily hold true as much. If you have passive scalars, and temperature is kind of a in between, but if we have, say, water, and if we have CO2, methane, flux, this works all with the same underlying footprint models and methodologies. It's different though, if you want to not look at flux, but if you want to look at concentration or abundance, like a temperature field and how to trace that back where it's coming from. And the reason is that if you look at, let's say with CO2, if you look at CO2 concentration, that has forever memory. Like, yes, it bounced off that tree here 2 minutes ago, but before that, it bounced off the city building and off that smokestack. And, it has essentially an infinite imprint. And that infinite imprint, it's kind of crazy in the way you think about it, goes back forever in time. But, anyways, that infinite imprint is being reduced to the last bounce, to the last time it touched the surface with the eddy flux. And why is that? Because the eddy flux, eddy covariance, it subtracts the average. It subtracts the background concentration. It subtracts the background wind, for example. That's how covariance is defined. And that's how we essentially get the last interaction with the surface, which is why this is fairly well defined when we use it for flux as compared to concentrations. So with concentrations and temperature, you have to be more careful. Does that answer your question, Leila?
Yes, thank you, Stefan.
Yeah, you bet. All righty. So I think mine one was able to read in 5 minutes. Is anybody not here yet? Does anybody not have yet access to the data in their interface? All right, good. Time well spent then. Dave, do you briefly want to, you prepared those sections. Are you comfortable briefly talking about those?
Yeah, sure. I can talk to this. So here the data were provided as matrices of the fluxes, but they were defined at this bounding box. And so we tried to overlap with the 6 by 6 kilometer grid that we used for the extraction of our Landsat and MODIS data. And so in this step, we're basically taking the coordinate information. So the lower left X coordinate in UTM CRS or coordinate reference system, and then the lower left coordinate in the Y. And then we know that our resolution here is 20 meters. And so the nice thing about UTM is that it's actually measured in meters. So it makes it fairly easy to do the math to determine our coordinates of each of our cells. And from that, we can apply it to our matrices and define those as geospatial rasters. And so that's basically what is happening in this step, taking our flux matrices and turning them into rasters of the fluxes. And if you go down, yeah. And so then after that, I'm just basically printing plotting the first 5 of these flux rasters, just to kind of give you a snapshot of how that changes over, the first 2.5 hours. So every 30 minutes, we have one of these flux maps.
So, and I think it's important to make thanks, Dave. I think it's important to make a distinction here now. While those look similar and have the same extent of the maps that we created ourselves with the EVI relationship earlier, the EVI relationship earlier, that was an average over 1 week that eventually we thresholded to satisfy the EVI range of the training data. So we had 1 image per week. This was based on temporal data. This is now a complementary approach. This is now using the flux footprint modeling. It's tracing back the individual flux parcels to their origin, is allocating it there, within that same map extent. And then what you get is a map every half hour, which is what you see here. And here, this is nighttime right now. We see a little bit of patterning here, and the color range will essentially invert if we were to see daytime here as well. You'll see that in the summary map, because what we're going to do now, we have 1 map every half an hour. So in the next step, in order to be comparable again for the entire week, for the approach over the entire week, we're going to summarize them. We're going to stack them over the entire week. So 7 days, 48 of those maps in each day.
So I just want to point out too that if you wanted to see the patterning that's occurring over the full day, then in that animate, the animate command in this last script, you could change that to 48, or and that would give you a full day, and you could see the evolution of the pattern of the flux across the landscape for the full day.
So we could do kind of 25 to 30 should be midday.
Yeah.
Yeah, and now you actually see where the sequestration is occurring throughout the day here. So this color range is already changed. All right, now on to the next part. Now we want to stack them throughout the entire week, which is what's happening here in that next code box. And what's interesting is that some of these daytime and nighttime patterns seem to cancel each other out. So there's still areas of higher and lower productivity. What we also see is that the range here in terms of productivity is actually shifted lower compared to the weekly, the map that was done on the weekly data product. And one potential explanation for that is essentially that all that it took to create this map here is 1 week of data in the summertime during leaf on with during a high productivity season, essentially. So, very specific to that time period. Whereas the map that we did previously with the linear relationship, I'm going to scroll up here. This map here, it took 2 years of data to create until we found 16 coinciding remote sensing scenes that we could build our linear model on to then get a map for a week. So we needed 2 years of data. Essentially, we need to have our tower out there for 2 years to be able to create that map. And that also means we have 8 seasons in 2 years. So EVI changes during that time period, not only as a function of land cover, but also as a function of leaf on, leaf off. So we have all these other effects. The less productive seasons of the year are all folded into this here that might not necessarily apply as closely specifically to that 1 week period in August that we're looking at right now. And so what you see here, that the range is shifted slightly higher, that color band here. All right, now I should get down again. All right. Now the data is being reprojected. I think that was also part, Dave, that you put together that I found super useful. Do you briefly want to talk about that? The
Sure.
reprojection?
Yeah.
I think just these commands are really useful.
Yeah. So when we're trying to compare two rasters, we need to ensure that they're being projected in the same coordinate reference system and that they have the same extent. And so to do that, the Terra package makes it really nice to be able to reproject one raster to fit to another raster. And so that's basically what I'm doing here. I'm reprojecting the mean flux raster to align with our Landsat and our MODIS rasters. And in that way, we can ensure that any mathematical operations that we apply to them can be applied without issue. And so I will point out that the Terra package and that the project function uses by default some either nearest neighbor or bilinear relationship, I forget which one it is, to allow it to be able to reproject the data. So just be aware of that, and if you might want to change that depending on what you are trying to do with your analysis.
So what happened here essentially is we came from 20-meter resolution up here, and we now want to marry that with a 30-meter resolution remote sensing data product. So we had to bring it to 30-meter resolution, which Dave was encoding as part of this raster package here. So super convenient. And same for MODIS. So now that we have all of them in the same raster grid, essentially, what we can do is we can take a look at the pixel-wise relationship. So we do have 1 week flux map by tracing individual fluxes back to the origin. And we can relate each of these pixel-wise originating fluxes to the coinciding EVI or other remote sensing index, which is what's happening next here. So if you're evaluating that, and now there's a stark difference. Previously, we had 16 data points. Now we have about 60,000 data points in there because that's the amount of pixels that you have to now infer relationships, which is why we're showing this here as a density plot. And so what you essentially see here, there seems to be a lot more going on than just EVI when you look at the density plot. So what could be potential other controls on the CO2 flux other than greenness on NEE specifically? So whole 24 hours. Any thoughts?
Temperature.
I think Dave has it.
I was just thinking about, because we're using this indexes like NDVI that measure greenness, sometimes for needle-leaf coniferous forest, because they are evergreen, it's maybe not the best way to search for the relationship between flux and remote sensing. Maybe we could use other indexes that measure other pigments, like carotenoids, or I don't know, PRI. Probably, yeah.
Thank you. So we had one mention here on site maybe other remote sensing indices could load better on the carbon flux. We had a mention online. I think somebody was talking about temperature. Could you expand on that? So temperature, when you think about nighttime respiration, for example, which is part of any net ecosystem exchange. So we're not looking at GPP here, not just daytime, quote unquote, daytime cross primary productivity and relating that to greenness indices, for example, but we have nighttime in here as well. Why would we think that greenness in any way reflects soil respiration, for example? And so there's various other controls in here, and we have a whole list here where this type of tracing individual fluxes back to their origin actually allows us, provides us the data foundation, the statistical power to now start exploring what are other co-controls that in the previous weekly averaged over 2 years approach was essentially completely averaged out. So, you know, each of these pixels was just heavily averaged. So you don't actually have all that information retained anymore. And so here is a few things. Do different land covers play a role? So do different land covers actually have a different relationship with vegetation indices? So that could be one thing. Temperature regulation of nighttime respiration. So thanks again for the online comment. There appear to be data sparse regions for lower greenness values. So see here, there's not a whole lot that we can actually say. Again, this was only made from 1 week of data as compared to 2 weeks of data. So what about we look over an entire season, for example, or an entire month? Dave? The time?
I was just saying, like, this was a week of data versus 2 years, right? So that's
right.
Quite a stark difference.
Right. And so there's various options that we now, with great statistical power, also now have the great responsibility to explore and to control for. And that's essentially our vision as a jumping board for the next workshop, to then come up with approaches that are not just spatial or not just temporal, but spatio-temporal, and bring in machine learning and bring in these pieces together and explore how we can describe these controls. Yeah, plenty of motivation to get to the bottom of this at our next upscaling workshop. All right, any thoughts, any questions here before we head into another break? All right, well, thank you so much. We're only 6 minutes overdue. I hope that's still all right for our caffeine levels. Thanks for coming. All right, so we have a 15 minutes break, and then there's
Please be seated. Thank you. Stefan?
Okay, everybody, I'm fully aware that I'm the person that's keeping you from lunch. So we're going to work through a lesson on working with ZAR libraries. And these are the same ones that are hosting these data that I'll describe briefly as people get set up with their Google sessions. So everybody should be invited to interact with this notebook, this Google Colab file here. It's under topic 3. If we go to our, if we go to Google Drive, under shared drives, 2024 workshop, hands-on sessions, topic 3, code. So this file should be in there. And as before, we're going to go file, save a copy in Drive. you're going to please work with that local copy. Most people here have only view access to this file. Some people have edit access. And you do want to certainly be able to, run the file and work with it. We're going to be working with the data that we've created to try to provide a near real-time estimate of gross primary productivity using a workflow that we call ALIVE, the Advanced Baseline Imager Live Imaging of Vegetated Ecosystems. And someone's having me in the chat. Oh, sorry, that's different. Okay, so what we're gonna do basically is like learn how to interact and work with the data that are making up these 5-minute estimates of carbon uptake. So this is yesterday, what you're seeing here on the screen right now. These are our estimates of carbon uptake across the CONUS scene yesterday. The CONUS scene is the US plus Southern Canada plus all of Mexico and a lot of the Caribbean. From GOES 16. This is a geostationary, so weather satellite that's positioned basically above the tri-point where Ecuador, Peru, and Colombia all come together. That's what we think happened for carbon uptake across CONUS yesterday. You can see the remnants of Hurricane Beryl, which is now obviously not a hurricane anymore, kind of passing across the central United States throughout the course of the day, clouds elsewhere. Lovely day in California over here. It was obviously probably a pretty nice day up there in northwestern Canada. So if you think about what we're doing here, right, what the data that we're looking at is far more time points than Landsat makes in a year. About half the number that MODIS makes in a year, all in one day, right? So the volumes of data that we're working with are pretty extreme, but moving forward, right, as flux scalers, we need to start getting really used to working with kind of up-to-date data formats, as well, really importantly, working with cloud native workflows, okay? Because there's so much data and so much to do with it that moving those data around, right, is going to be a huge limitation. We need a system where we can interact with data where it exists, and that space is the cloud. So back to the file, right, if everybody, I have a lot of hyperlinks here describing all the different Python libraries that we're using, describing our workflow. We have a preprint that just came out a few days ago that describes some of the, what we feel are the highlights from our work here. But first and foremost, right, we're gonna go ahead and import, right, run the button here. We're gonna import NumPy, Pandas, Matplotlib, a lot of the very standard Python libraries. I have links to what all of those things do and what they mean for those of you who don't use Python, or if you're new to Python or just starting. The other thing down here that we're going to do, and so that when you run this code block 1, that should be about instantaneous. Running code block 2 should take a few seconds because we're going to install a previous version of a library called fsspec, which is something that we're going to use later on to grab imagery from Google Cloud Platform. And the reason we're grabbing that imagery is actually just to steal its geographic coordinates to do a projection of our data onto the same geostationary grid. So this third block here, we're going to have to install Cartopy and MetPy, and these are for projections, right, and for meteorological data. So by having these two libraries, we have access to a lot of geospatial plotting functionality that's obviously going to be very useful later. So what we're going to do now, and what's going to take about half a minute, probably, is to run code block 4 right here. And that's to install ArrayLake. And so as we're doing that, right, hit that block, you're going to, and I've hidden the output, it's going to show you, oh, actually, there's going to be an error message in one of the previous blocks. Just simply ignore the fact that there's an error message. It's not consequential. Right, this is an error that actually isn't an error, just ignore it. When this fourth code block executes, it's going to ask you to go to a link to get an authentication code. So please just go ahead and get that code from the website that you'll be prompted to go to and paste it in. So as people are doing that, I'm going to quickly go and step back and talk a little bit more about ALIVE and what it is, right? I wanted to get people started. Is everybody on board, right, with where we're at right now, just installing the different Python libraries, everybody online, thumbs up, just put something in the chat if not, and just raise your hand if not. There's going to be a couple instances where things are going to take a minute or two to run, and at that time I'll run around the audience and interact with people online and make sure that everybody is up to speed. So the Advanced Baseline Imager Live Imaging of Vegetated Ecosystems is a project that's funded by NSF and University of Wisconsin and USDA, mostly with data from Ameriflux and Neon. They have a really fantastic team with Danielle, Sophie, and Sadeg, who really made everything happen. You know, we have this idea here that there's no reason that we can't bring fluxes into the present tense. Right? We're always working with fluxes from the past, which we can learn a lot about. Right? We can learn a lot about the Earth system by studying what's been measured before. And we can learn about how the world is going to work by thinking about what's going to happen in the future. But a lot of environmental decisions are made, right, with the information that people have right now. And the more we can make ecology present tense, the more we can interact with managers and hopefully be better stewards of the Earth system. At least this is my theory. My theory also is that people have spent their lives looking at weather satellite data. People have looked at meteorological data forever. And as a consequence, they know what it means. And if we can put water fluxes and carbon fluxes in that same framework by which people watch the weather, right, we can perhaps have a nice avenue to communicate with people how our Earth system works. So the way Alive works is we took data, and there's a preprint with all these, well, not a preprint, a scientific data publication with all these data by Daniel Losos. And we also took all the different data products from GOES-R. So it measures top of atmosphere reflectances and radiances, brightness temperature, strictly speaking. There's a lot of inferred surface products for reflectances that it creates. And we and the Alive teams have also created critical inputs like downwelling shortwave radiation and other things. We're actually also working on land surface temperature. So basically, long story short, we've built a data set that uses from each eddy covariance pixel all of the flux data and all of the GOES data. And it uses machine learning models to have a statistical representation of what geostationary signals correspond to what flux and where. That data set, Daniel Losos et al. 2024 in Scientific Data, are data from these 314 eddy covariance tower locations, of which we could only use 126 because of data latency, right? Our surface products from GOES 16 only started in 2021, and most eddy covariance towers do not have data from 2021 onward. So much of the data is back in the past. So of those 126 sites, right, we trained machine learning models to create using this workflow and then built it into this workflow. The machine learning models, we use gradient boosting models. They are not meaningfully worse than other approaches, but they're about an order of magnitude faster. If we're to make a prediction every 5 minutes using these volumes of data, it has to be fast. If our workflow is longer than 5 minutes for every step, we're always going to be falling behind. So right now we're at about 2 minutes. That's fine. We use all of the data that is housed in Google storage and public S3 buckets. That includes a lot of data from the GOES 16 satellite, the Advanced Baseline Imager thereon. And with that, right, with our model, we then add layers to a growing ZAR array. So you can think of a ZAR array as like a cloud native 3-dimensional chunk of data. But unlike a data cube, right, we're always appending to it and adding to it without having to rewrite it. And we're also not having to move it. Currently, it lives on University of Wisconsin S3 object storage buckets. We're coming to learn that that is a bottleneck for getting you the data, which is why there's going to be some slightly longer runtimes than we're going to hope for as this goes forward. As a consequence of this lesson, we're going to actually move our data to different storage buckets to have the data be closer in the cloud to where the process, where the compute is taking place. So with that, right, critical for this this part of the project is the array lake, right? That's created by a company called Earthmover, and Orestes, who's right here, waving his hand and taking a picture, is one of the chief engineers for Earthmover. It's a really fantastic startup, and one of the reasons it's fantastic for us as Earth scientists is that it's basically run by Earth scientists who have the same problem with massive volumes of data and know a lot about ocean science and atmospheric science. These are people who are professors at Columbia, who have worked for NCAR, who are very familiar with the types of Earth science problems that we face every day and are rapidly finding solutions, right, to make these enormous volumes of data more accessible, right? Because we're way past the big data era. We're in the extreme data era. And I always think back to something that Dennis Baldacci talked about a long time ago, where, once FluxNet started, we were like the Human Genome Project, except we had far, far, far more data. Okay, so eddy covariance and FluxNet has always been at the cutting edge of environmental big data. And to stay at the cutting edge, I'd like to think that we really need to learn how to, as a community, work with sort of cloud workflows and cloud native data formats more readily. So really quickly, the model works well, but not perfectly. We can look at all sorts of cool things like the impacts of the eclipse. And going forward, we're going to be working more and more. This might take a second. Should be able to see the eclipse if you go to that file, with also water flux data. And we're also going to work our hardest to basically take all the fluxes that we measure and make them as real time as possible. So back to the matter at hand, which is this Colab notebook. We have here code chunk 5, and this is going to define our repository, right? So we have a repository called Alive version 1 2024. Obviously, our version of Alive now is an alpha version. We're going to try to make it better and better. But that ZAR array still is library, I should say. ZAR library is still living in this S3 bucket, and it is fully accessible to you. Now, when it comes to the next part of the code, why is this not? Okay, these chunks, and why this isn't, oh, here we go. When it comes to this fixed grid to lat long functions, these are a number, yeah, question. What's happening? Number 5, did code block 4 execute successfully? And are you using your Google, account for all of this project? Yes. So what I did, and this took me a long time, is I individually entered everybody's email that you initially provided and then separately all of the Google emails. So everybody's email should have access to the repository if it's Google. Yes. With Gmail. Oh, sorry. This needs to have the read only equals true. Oh, right here, read only. Yeah, okay. I had to make so many different versions of this because to move it into University of California's Google file was way more difficult than I thought it would be. There's all sorts of permission issues. Where does that need to go, Orestes?
The second line in the cell.
Right here?
So right up here.
Oh, that's read only equals true.
Yeah, if you add a comma.
Read underscore only. Okay, well, this is right here. So put that little block there. Yeah, that was mentioned. We made that fix a day ago, and then I actually was drawing from previous files to rebuild this file this morning to make sure it worked for a number of reasons. When you put read only equals true, take a second to do that, and let's see if it works for everybody. Okay. It's working here. I see some things in the chat. Okay, works for Layla, works for Gabriella, thanks. Yeah, okay, cool. Okay, thanks everybody online, and thank you for reminding me that I had taken that important piece of code out of the code accidentally. Working okay now? Okay, thank you, Restus. This fixed grid to lat long functions, you can just run all 7 hidden cells here with no consequence. If you want to dig in and learn about what those things do, they're basically mostly just reprojecting standard coordinates into geostationary coordinates and some other functions. So we're just going to run all of those things at once. And then this next little line, make time series line plot, this is where we're running into a little bit of a read issue. And so what we're going to do to start here is I'll show you the output, which is here in the file, but we're not going to run this thing through because it's going to take so long. Instead, what we're going to do first is run what currently for me is cell block 32, and whatever block it is for you, the geographical coordinates of the Underk neon tower site. That's going to be its latitude, longitude, and elevation. And then we're also going to, because we're going to try to be a little bit patriotic, work with data from the 4th of July. And by the 4th of July, I mean last week, okay? 2024, right? We're trying to make things as present tense as possible with all the fluxes that we're working with. So if you run that, and then you run this little convert your point from latitude, longitude to ABI fixed grid, this is going and dipping into these kind of hidden functions that I asked people to run and put things into geostationary coordinate projections instead. Has everybody followed along so far? Cool. This is great. It's like if everybody here was like in my class, I would be like so much easier, man. So I'll encourage you to enroll at the University of Wisconsin-Madison and take my data science class. That would be a dream. Okay, so the next thing we're going to do here is hit this button here and extract some time series data from a given point. Now, what we're actually going to be doing is using these data subsequently to create some maps, some individual time slices of our ZAR array, because these things are moving pretty quickly, but right now, because of a UW problem, which we just figured out this morning, is taking a little bit longer. The upside is if you'd like to make that time series plot, you can just do it over lunch, and by the time you get back from lunch, it'll be there. So don't run this line. It will throw an error because of what we've masked out. We've masked out this thing called DS Daily. Leila, that is a really good question, ABI angle. So Leila online, if you go to fixed grid to lat long functions, and you can either individually execute all of these code blocks or just hit that button and execute them all at once, that should be what you need, right? All of those, and what you wrote made me think maybe there's a typo that got introduced somewhere, but it looks like it's not. That could just be elsewhere. This just does happen to be what that time series looks like for our estimate of what's happening at that tower. Right now, we could compare these data against those tower data. The data set was trained based on this site, but wasn't trained on data from the 4th of July because data from the 4th of July wasn't posted yet onto Ameriflux or Neon sites, right? There's still that latency issue, okay? The data still take a couple weeks even with Neon to get here. And with Ameriflux, it's oftentimes much longer. And a major reason, of course, is individual PIs, of which I'm a guilty party, take a long time to actually send our data to Ameriflux. So to make things real time and to make things have lower latency, right? We want to bring all the data, all the information that we can together, and then learn from it, either with our statistical models here or with a more physical-based machine learning or environmental model of our fluxes. So what we're going to do now is create an image of a single slice in time. And that's going to be right around noon time. And that's going to be in the central time zone about 18 UTC, okay, London time. So, and by say about noon time is that the scan times is every 5 minutes, but that's actually 2 minutes, 7 minutes, 12 minutes, 17 minutes. So we're going to do a little bit of a time approximation. It's actually going to be about 2 minutes after 18 o'clock. We're going to run this little chunk of code here. That shouldn't take any time at all. And then here's going to be a little bit of a hack and some trickery, right? Because immediately information from the geostationary satellites and so many other satellites, once they become available, enter Google Cloud, right? We're going to steal one of those files. We're going to steal one of those files and we're going to grab its geographical information. This little hack keeps everything cloud native. We can easily store all the geographical information on our individual computers and then ask for it and then get it and then connect to our Google Drives and do all that stuff. But the data are already on the cloud and we can just go and freely get it. So we're just going to go ahead and do that. What do all of these things mean in this exceedingly long URL? Well, this is just goes 16. This is just happened to be day of year 164 in 2022. This happens to be for a particular time point for one of the particular data products that happens to be the bidirectional reflectances. So that's a little bit inconsequential. We're just getting latitudes and longitudes. And now, and this might take a minute to run, in fact, a minute longer than it did before, we're going to run this chunk of code right here that we're looking at now to get this output. So this is at noon Central Time, Standard Time, not daylight savings, et cetera, et cetera. I always tell my class once a week, time is a pain in the ass, okay? Time is a pain in the ass. So it's gonna be noon-ish, and you're gonna see what I saw in a little town on the Wisconsin side of the border near St. Paul, Minnesota, where I was on the 4th of July. Well, this is actually the 5th of July. Someone changed that, but either way, long story short, we can make that the 4th of July if we need to. Man, it was cloudy. It was a wet and rainy day that day, as it happens. So you can see those clouds and you can see what we infer are those impacts of those clouds on carbon uptake processes at that moment. So somebody has a chat in the chat. Boop. Oh, how to fix the name error. Yanjua, I think what needed to happen here with there shouldn't be a name error, but it is important that you run, yes, Sophie, thank you for helping. Oh, Sophie, Danielle, and Sadeg are all online helping with chats, and thank you for that. And Orestes, thank you for being here. If you run the fixed grid lat long functions like Sophie mentioned, that's probably what you need. Okay, so if you run this chunk of code, it might take a little bit of time, but you should result in this image. So everybody go ahead and do that. And what I'm going to do is walk around, and Sophie, Danielle, and Sadeg are going to snoop online and answer any questions and see if people can correctly plot this image. Because what we're going to do next is do kind of a daily aggregate. Then we're also going to make a movie. Okay, we're going to basically connect to our Google Drives, run a loop that will append individual images onto each other, and at the end of the day, have a little movie file in your Google Drive for you to check out at your leisure, and or change the parameters, change the dates, change the geographic location to an area that you might be more interested in, and do it by yourself. So I'm gonna walk around now and make sure that this is working for everyone. Please send. It's here. I'll write it up. Look at this. I'm just gonna do it. Use Word. pcstoy@wisc.edu. Send me an email. Word is taking forever to run. Here, pcstoy. Yanjua, yep, and Joyce, and I got yours. That DS daily, okay, yeah, don't run that chunk of code. We skipped that because that was taking a little too long. And the reason it was taking too long is because of where we're storing our data at the University of Wisconsin. And in effect, what we figured out this morning is that the input-output speeds of those buckets, because they're connected to the cloud, but they're not cloud optimized. Right, they're not cloud optimized, meaning that they are not close enough to where the compute is taking place to take full advantage of cloud computing. Does that make sense? Okay, so let's see, token. So I'm going to add a few people's info here. And for others, you can kind of continue on the lesson because I need to go and find out how to, let's see, go back to Slack here. Boop, 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 boop. Okay, boom, 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 boom. Blah, blah, blah. Okay. So Bridget, yeah, good question. And Orestes knows most about this. What we're doing basically is right now ArrayLake is providing their services for free, which has been wonderful for us. And then in an NSF grant that we just got recommended for funding, which means it'll be funded ideally on August 1st if everything goes as it should, we've added to the contracted services budgets what we feel is a good fee for service. So because we get a lot of technical support from ArrayLake, we essentially had kind of a nice trial version that worked out very well. And now we're essentially going to start paying for the service because time is money and they've offered us an amazing amount of time and technical assistance. So only fair. So that, yeah, Bridget, that's a really good question. And
Yeah, thanks.
Oh, sorry.
So it sounds kind of like it's like the paid AWS cloud compute or something along those lines, but it's more about moving data around.
It's more about creating the metadata necessary to have ZAR libraries that are readable. Is that
I see.
Orestes'
Okay.
explanation?
Yeah, thank you.
Describe it as a way to manage your scientific data.
Yeah, as a way to manage scientific data. So it just online, they might not be able to hear this. I'm going to repeat what you say.
So the data itself right now is living in your own cloud. So it's not hosting data for you. But when you connect it to the ArrayLake, you have a bunch of features on top of that. The first one that we're looking at right now is the data catalog. So this lets you.
Oh, actually, Orestes, can I give you the microphone so that the people online can hear? Where is the microphone? Nicola, do you have the mic? Oh, you can just talk right here too. Okay, cool. Go ahead.
Yeah, so right now we're looking at the ArrayLake dashboard. And this essentially is giving you a catalog on top of your scientific data. So any of your climate data, your ZAR files that are stored in S3 are connected to our platform. And so in the notebook, as you saw, you can use our Python client or API to interact with that data. And what this is essentially giving you right now is the ability to version your data, to manage access to your data. So as you've all seen, we created user accounts for you and then tied your users to this repository. Has everybody here used GitHub before or knows what that is? Yeah, so the model here to browse ArrayLake is very much like GitHub. We have repositories, and within those, you can put your ZAR data sets. And those are a hierarchy of different groups and arrays within them. From the web browser, you can also see, are you adding a member here?
I'm adding a member. I only have, okay, I see Julia's. Yeah, I'm adding members.
Great. So you see your demo here of just adding a new user that gets access to your data set. Often these types of databases and catalogs have to be built from scratch and everything has to be re-engineered. And that's usually not a climate scientist or a data science team's primary strengths or concern. They're more interested in getting straight to the data. And on top of that, right now, we're working on a lot of features that will help optimize access to the data. So your ability to essentially get in and get work done will be very much accelerated using versions of your arrays that are managed through ArrayLake. You can learn more at earthmover.io or talk to me. And maybe in a second, we'll just take a look at a live workshop repository here.
While we're here, let's do that.
Yeah, so
This is in Safari, Google, Chrome.
Yeah. So we're going to go to the Whisk Alive. And so let me just close some of these windows here. Yeah, sure. We're just adding a couple more users here.
Okay. Email users. See, yeah, this is
It's just opening your email client, right? Yeah.
yeah, I know. I was having
Yeah,
trouble.
let's go back to-
Steel Lab Workshop one.
Mhm.
I was having trouble copying it directly out of the.
Gotcha.
Doing some of the things on this actually opening emails here. And I'm taking it right from Gmail, which is what I've done. Oh, yeah, Danielle, you can add users too. Thank you, Danielle. Okay, so
Yeah,
back to
great. So I'll,
you can close the chat.
perfect.
We can minimize this too, actually, sorry.
Yeah, there we go. Great. So this is the kind of homepage when you log into your account. So we have the Wisconsin Alive organization, just like in GitHub, you might have an organization. This is where all your members live, and they have access to the various data sets you have. So right off the bat, we have this dashboard that's showing you how much data you have under management total, how it's grown over time, the read and write on the data, and also the commit activity. So like I mentioned before, you're able to create versions of your data sets, and that's done by committing to the data set just like you would with code. So our data sets are immutable. So you're able to kind of time travel back to a different state of your data. So if you're trying out something new in your code that produces data in a different way, and you decide that's not the direction I want to go, you can always roll back your data set to where it was previously. Looking through here, you can get a list of your repositories. I mentioned before, the one that we're interacting with today is been flagged public, so anybody that's on ArrayLake can access that. So
Mostly tests.
yeah, we have a lot of test data sets here. You have some feedback on the status of your data set. And in the future, we want to make this public also open to the internet for orgs that want to share data kind of anonymously to anonymous users publicly. And when we go into a repository, I think just a little slow on the internet here. There we go. You're able to see the overview of what is actually in there. So we have in this ZAR file, we have one group or one array here with one group with actually 5 arrays. And so we can see the GPP array, and you can right away go ahead and browse what the details of that array is. So we can see the chunk schema being used, the overall shape and the different dimensions and variables and coordinates. You can also, you haven't done this here, but you can also add attributes, and those attributes are searchable. So you can find rich metadata that often comes through here. If you're following a certain standard, a spec like that will also be displayed properly in the UI. So instead of having to like launch up a Jupyter notebook, write code to figure out what's even in this data set, are the variables that I'm looking for here, you can just do it through the web UI. You can share these links with colleagues and collaborators so that they can have access as well. And then we also have the history tab here that shows you the commits that you've made. You can also create tokens that can be used for different processes that you might have in like a pipeline to interact. So it doesn't have to be just logging in with manually through your username. You can have some type of API key accessing all the data that you like.
And the rest, if I can have, if you look at these quickly, here, like, you'll see what those commits are is that every evening we just add 192 time slices as a kind of a big block of data to append to this growing ZAR library. That's what the commits are. So this automatic and SSCC is the Space Science Engineering Center at the University of Wisconsin, where a lot of sort of initial geostationary weather satellite data have been created, archived over time.
I think that's a good overview for now. If you have any questions about ArrayLake or Earth Mover, just come talk to me and happy to chat with everyone.
Yeah, thanks, Restus, for that. That was great because really quickly, earthmover.io. The thing that is really cool, do you see that little purple thing in the background? So Ryan Abernathy is the CEO of Earth Mover, really describes it as this, right? We have data that's like one big block, and then people are oftentimes taking lasagna, right? Just that one slice in time. And then here in eddy covariance, we're taking spaghetti. We're taking one pixel across multiple time points. One of the things that Zar libraries do so well is make it able to chunk data into ravioli. So discrete little parts of space and time that can help for regional analysis and scaling and focusing, zooming in on the time and area that you're interested in. So it's really the structure of the Zar libraries has a nice analog to how we oftentimes want to actually work with geospatial data as fluxers. Okay, back to the matter at hand. So we created this, and if you haven't in those online, thanks Danielle Sadek and Sophie for helping out. The other thing that we can do, right, 5-minute data is probably too much, although it does capture a lot of those nonlinearities in carbon fluxes due to cloudiness that we're trying to better estimate and avoid those Jensen's inequalities. So we have here some code that grabs a start and end period, masks out those starts and ends, and then Danielle came up with this, but kind of this clever sort of chunking approach to help speed up a daily aggregation. So when we do that, right, and we sum those data, and that should be, ooh, this isn't, sorry, this is an earlier version of the file. There is actually a unit conversion factor to move it from 5 minutes to daily. We have, in effect, if you run these lines of code, and it'll take a minute, the ability to do kind of a daily average of all these data. And you can also obviously average over longer periods in time and average over certain regions as you see fit. Average or sum or perform the operation that you're interested in. Okay, so I'm going to look really quickly at, there was a lot of things in the Zoom chat. Why am I not getting to the Zoom chat quite right? What happened there? Well, completely missed the chat. But okay, long story short, we'll get back to this. And the other thing that I really thought would be interesting for people to do is create a movie file, right? If we can, oh, there it goes. If we have the ability to grab slices of data, movies are just frame upon frame upon frame that's rendered at a speed that our eyes are comfortable with for being able to recognize what's happening. So the way that we can do that is simply define, right, a start and stop period. We're also going to look for a geographic area of interest. And so this is basically the Western Great Lakes states. We're going to zoom in on that area that includes the Underk Neon eddy covariance tower in the Upper Peninsula of Michigan. We're just going to quickly, in the pandas datetime format, sort of have define a starting time and a stopping time. And then we're going to say, okay, we're just going to run a loop. It's just going to be for 2 hours. Okay, it's going to take all of these slices. And if one person is running this, it should take about 4 minutes. But when 100 people are running it, it might take a little bit longer, just as a heads up. Something we're going to do here is that we can't really render movies in Colab unless I'm completely missing some of its functionality. So what we're going to do here, and I see David nodding, I mean, I could be missing something. Maybe we can make movies and see them in Colab, but as far as I'm aware, you totally can't do that. What we're going to do instead is connect to our Google Drive, and that's what this little line of code is right here. And by doing so, right, we're going to give that movie a place to go and save it. And it's just going straight onto your main Google Drive, or not digging into anyone's folder structure or anything like that. So to make that movie, right, we're going to run a loop. And so here you see the Python loop syntax. So you basically just have a little colon here, and then you're just going to hit the tab button, and everything that's been tabbed is inside the loop. And we're going to loop through each timestamp. We're going to create an image, and then we're going to build upon and build upon and build upon that image, right? Add it to this movie file, add it to this movie file, add a color bar, and then save our animation, right? Save our animation with certain features and add each frame, and then save it to our path, which we've defined as simply our main Google Drive. It's that main folder. And the other thing that we're doing is printing out every single image as it's being added to our growing file that we're going to save then as a movie. So once you hit that video, you see here back in the day, it took me 4 minutes to run, and back in the day is yesterday. It will take other people probably a little bit longer to do this. So if you'd like to just do this and then go and enjoy some lunch and then come back and see how it works, that could be a thing. What will eventually happen, if I go to my Google Drive here, is a movie file that will look something like this, right? We have about 2 hours of watching the clouds go by on the 4th of July. The Underk site is going to be right around here, right? And so this is what we are thinking based on our machine learning model trained on eddy covariance data is our gross primary productivity for this region on that day over this time window, okay? So this is all of the code that you need to sort of do some basic visualizations, some basic summations, and I'm actually gonna, well, I'm gonna actually re-add some code that I had changed accidentally to make that daily sum better because of the conversion factor I didn't add. And then, sorry, there's too many tabs open here. Right, people are going to have the ability to interact with ZAR libraries, choose the data that you want, right? Think about how nice it can be to work with enormous data files. And also because, right, everything is here on the cloud, okay, is you don't even actually really even need very fast internet speed, right? You should, in principle, be able to perform these operations no matter where you are on Earth, as long as you have some connectivity, and not have to have huge computers to do big data analyses. So one of my hopes always is that this helps democratize big data and data science, right? By making it more possible for people, no matter where you are located, to do big science, right? Don't need supercomputers anymore. We don't need endless storage, right? We just need the ability to write some code. So that was what I mostly had for the lesson, with the caveat that I did gloss over some things, but it's also 12:26, and sometimes it can get really hard to dig deep when you're feeling hungry. So what I'm going to say now, with Nicola's permission, is lunch here. Lunch is here. Lunch is here. If people want to go and get lunch, I'm not one to stop you. I will walk around for the next many minutes to see if people are having problems or to answer any questions. And you might have an announcement really quickly first. Oh, the 2 talks. Oh, the lunch talks. Oh. Okay. Oh, I